When pilots talk about flying efficiently, the immediate assumption is that saving fuel simply means throttling back and burning less gas. But aerodynamic efficiency requires choosing between two entirely different, mathematically opposed targets. The first target is maximum endurance. This metric maximizes the physical amount of time the aircraft can remain airborne on a specific volume of fuel. Endurance is the priority only when covering ground is irrelevant. If an aircraft is placed in a holding pattern waiting for ATC clearance, the goal is to keep the engine running as long as possible over a single geographic fix. The second target is maximum range. Instead of optimizing for time, this metric maximizes the actual physical distance covered for every drop of fuel consumed. The physics of flight dictate that an aircraft cannot achieve best range and best endurance at the same airspeed. The speed that keeps you in the air the longest will severely penalize the total distance you travel. Mastering en route performance, a requirement for the commercial pilot knowledge exam, means understanding exactly how to manipulate the laws of aerodynamics to prioritize either the clock or the map. This diagram illustrates the baseline metric for distance, specific air range, or SAR. SAR measures the number of nautical miles an aircraft travels through the surrounding air mass per unit of fuel burned. In a perfectly calm environment with zero wind, the air mass is stationary relative to the Earth. Here, specific air range perfectly matches specific ground range, or SGR. Introduce a headwind, and that one-to-one relationship immediately breaks apart. The ground speed meter drops as the aircraft fights the opposing air mass, while the true airspeed meter remains completely unaffected. The aircraft is still burning fuel at the exact same rate per hour, but the usable ground distance covered per gallon is rapidly shrinking. Standard static performance charts assume a zero-wind environment. They cannot account for real-time wind vectors, leaving the actual specific ground range vulnerable to atmospheric conditions. To optimize en route ground range, a pilot must look beyond those static tables and mathematically alter their airspeed to offset the wind's penalty. This chart shows the fundamental physics dictating fuel consumption, the direct relationship between true airspeed and power required. Plotting power requirements across all airspeeds forms a classic U-curve. Flight requires immense power at very slow speeds to overcome induced drag, and immense power at very high speeds to overcome parasitic drag. The curve dips in the middle, identifying the speed envelope where the combination of induced and parasite drag is minimized. Looking at the absolute lowest point of the curve on the y-axis reveals a specific aerodynamic state. This nadir is the minimum power speed. It is the exact velocity where the engine does the least amount of work to maintain level flight. Because engine power directly correlates to fuel consumption, flying at this minimum power speed yields the absolute lowest fuel burn rate in gallons per hour. Holding the aircraft at this precise airspeed provides maximum endurance. While the fuel flow is kept to a strict minimum, the resulting true airspeed is slow. The bottom of the power curve ensures you survive a lengthy hold, but it's mathematically ineffective for efficiently traveling to a distant destination. If the goal shifts from staying airborne to maximizing specific air range, the target on the power curve must move. Achieving best range requires operating at the speed where the wing is most efficient. This is the speed for minimum total drag, known as the best lift-to-drag, or LD, ratio. Aeronautical engineers locate this specific speed geometrically. Starting from the exact 0, origin point on the graph, a straight vector line is drawn upward toward the power curve. The line stops at the exact tangent point where it just barely grazes the underside of the curve. Dropping a vertical line from this intersection down to the x-axis gives us our target velocity.
This point dictates the maximum range speed in calm air. Notice that this tangent intersection sits further to the right on the velocity scale than the nadir of the minimum power speed. This proves that the most fuel-efficient speed for covering ground distance is faster than the speed required simply to stay in the air. In a vacuum with zero wind, this mathematically derived tangent point provides the absolute best specific ground range an aircraft can achieve. The perfect mathematical model fractures the moment an 80-knot headwind is introduced. Because a headwind applies a direct negative force against ground speed, the geometric origin point of our chart must be adjusted to compensate. We shift the starting origin point of the tangent line exactly 80 knots to the right, mapping it directly to the headwind's magnitude. Drawing a new line from this shifted origin point up to the U-curve reveals a drastically altered flight profile. The new tangent strikes the curve significantly higher and further to the right than the calm wind baseline. The geometry dictates a clear directive. To maximize specific ground range in a headwind, the pilot must increase their true airspeed. This creates a paradox. Flying faster requires opening the throttle wider, operating higher on the power curve, and burning more fuel per hour. The strategy works because increasing airspeed reduces the total time the aircraft spends fighting the headwind. Getting out of the headwind faster saves more total fuel over the duration of the trip than the higher engine RPM consumes. When fighting a strong headwind, a pilot must actively increase their hourly fuel consumption rate to maximize their actual fuel efficiency over the ground. This table proves the theoretical curve shift using actual performance data from a pilot operating handbook, showing an aircraft flying at 6,000 feet. Look at the bottom row. At a low power setting of 48%, the aircraft flies at 138 knots. In calm air, this slow setting provides the highest specific air range, yielding 2.22 nautical miles per pound of fuel. This perfectly matches the first tangent line drawn from zero. But against an 80-knot headwind, the specific ground range for that exact same power setting drops to 0.94 miles per pound. Clinging to the calm air maximum range speed leaves the aircraft crawling over the Earth at a ground speed of just 58 knots. The engine is sipping fuel, but the headwind is extending the flight time so severely that total efficiency is ruined. Now look at the middle row, representing a significantly higher power setting of 63%, pushing the aircraft to 159 knots. Despite the engine burning more pounds of fuel per hour, the increased true airspeed pushes the specific ground range back up to 1.00 nautical mile per pound against the headwind. The inverse is also true. If the aircraft picks up a tailwind, the geometric tangent shifts to the left, meaning the pilot should reduce power and fly slower to let the atmospheric energy carry them further. Specific ground range is never a fixed number printed in a manual. It is a fluid target dictated by the wind vector outside the cockpit. FAA performance tables provide fixed values for specific engine settings and altitudes, but the atmosphere is entirely dynamic. These static charts only supply a baseline. The responsibility for real-time optimization rests entirely on the pilot in command. When flying cross-country, specific ground range is the ultimate arbiter of efficiency and profitability. The aerodynamic curves we've explored redefine the role of the throttle. It functions as a precision lever for balancing fuel burn against the time spent in a headwind. It is an instrument for managing temporal exposure. The power setting directly controls the mathematical ratio of time the aircraft spends fighting the atmosphere. Mastering these variables distinguishes basic operation from professional en route performance. By manipulating the power curve to account for the atmosphere, a pilot negates the wind's penalty, ensuring the aircraft operates at true aerodynamic peak.